Hello, everyone. Welcome to today's webinar. We'll get started in just a moment here. Hi, welcome to those of you just joining us. We'll get started in a second here. All right, hello and welcome to the second webinar in the 2023 National Seismic Hazard Model series that we here at EERI are doing in partnership with the US Geological Survey. It's great to have so many people and so much interest in this. My name is Elizabeth Angel. I'm the Communications and Program Manager at EERI. And before we get started today, I wanted to take a brief moment to introduce EERI to those of you who aren't familiar with us. The Earthquake Engineering Research Institute is the leading nonprofit membership organization that brings together people from a wide range of disciplines and backgrounds all around the world who share the common goal of better understanding earthquake risk and increasing earthquake resilience in our communities. So we have academics, researchers, practitioners, students, people at every stage of their career. We have a lot of opportunities for networking and professional development, for involvement in programs like post-earthquake reconnaissance. So if you're not a member, I really hope you'll check out our join page there, and I'll put that link in the chat later because we'd love to have you become a part of the EERI community. And I also want to acknowledge that the funding that makes it possible for us to do free public webinars like these comes in part from a FEMA grant, but also from the Learning from Earthquakes Endowment Fund and from EERI members. Additionally, I'd like to acknowledge our subscribing members, particularly our visionary subscribing member, Computers and Structures, Inc., and all the other firms and organizations listed on these two slides. Their support helps us run our programs, institutions, and also creates a lot of great opportunities for EERI members, so we're very grateful. Then finally, we have some great upcoming webinars as well. We'll have one on the 14th that is hosted with the Applied Technology Council that's going to focus on the NAHRP circular about post-earthquake investigations and about coordination, collaboration, and participation in those activations. We have one on the 15th that's going to be hosted by our Northern California chapter. That's a quick quake briefing looking at the recent earthquake swarms in Southern California, but particularly the role of shake alert in those. So that'll be again featuring some great USGS folks. And then we've got one scheduled in June from our San Diego chapter that's going to look at liquefaction triggering. So we're also, I think, working on a sort of reconnaissance and findings webinar about the recent Myanmar, Thailand earthquake, which we don't have pinned down on a date yet. But I'll put a link in the chat to the events page on our website where you can find information about all of these and register for them. So on that note, I just wanted to introduce the speakers we're going to have today. We have some introductory remarks from Bob Pekelnicky, who's a senior principal at Degenkolb Engineers. So he's going to open us with those remarks in a moment. I want to just note before we do that, that you'll be able to put questions in the Q&A tab on your Zoom control panel. If you look at the bottom of the screen, you'll see that little Q&A icon. So you can submit questions there in writing throughout the webinar during all the presentations at any point. And then at the end, after we've had all the presentations, we'll come back and we'll have a Q&A session to respond to those. So please remember to put your questions in the Q&A, not in the chat. And then because after Bob, we'll go straight into the presentations, I just want to briefly introduce our great panelists today. Sanaz Rezaeian, Nicholas Luku, Andrew Makdisi, and Kishore Jaiswal, all of whom are research structural or civil engineers working for the US Geological Survey. So I'll turn it over to you, Bob, now. And you want to unmute, please?
Yep, thank you very much. I was just in the process of doing that. Welcome, everyone. Thank you for spending your morning or afternoon with us for what I think is a really important topic to talk about, which is the engineering applications of the USGS's National Seismic Hazard Model. You had a really great overview of all the research that goes into this model in part one. And now we want to talk specifically about how this goes and directly impacts the design of buildings throughout the country. So I think a lot of the practicing engineers that are on this webinar are very familiar with the ASC 7 hazard tool. You put in a latitude, longitude, a building address, whatever information you have, and you get out the design information that you need to provide the seismic design through chapters 11 through 22 of the ASCE 7 standard, which is referenced by the International Building Code, which forms the basis for most state and local codes throughout the country. So I want to draw your attention, if you're not familiar or if you haven't been practicing long enough to know that previously, this information was only available through the USGS's website. And the fact is, all of the information, seismic information you get from the USGS or from the ASCE 7 hazard tool is based on the USGS's National Seismic Hazard Model. And that information is actually just querying a more complicated web portal through the USGS website. So this is really the fundamental bedrock of seismic design in the United States for both evaluation and retrofit of existing buildings and new building design. And it has been the case since the 2000s. A really monumental project culminated in 1996 with the publication of the National Seismic Hazard Model that is the basis for what we use now. And that seismic hazard model was picked up by a joint USGS FEMA work project called Project 97, which then led to the recalibration of seismic design parameters from zone parameters that were based on earthquake zones to the specific seismic hazard parameters based on the exact latitude and longitude of your specific project site. This informed and changed ASCE 7 starting at the 1998 edition and was picked up in the 2000 International Building Code. And since then, this process has played out. Each time the USGS updates their hazard model, the new hazard model is then handed over to the NEHR Provisions Update Committee, and that they decide whether to accept the hazard model. And then once they've accepted the hazard model, it goes on to inform the next edition of ASCE 7. And then that edition of ASCE 7 is picked up in the building code. So essentially every 6 years, when a new USGS seismic hazard model comes out, it then informs and updates the building code provisions, once again, impacting how engineers design buildings. And also it is picked up in the ASCE 41 standard for how engineers would evaluate and retrofit existing buildings. So with that introduction, I'm going to turn it over to the first of our esteemed panelists, Sanaz, who's going to talk about the current evolution and building code adoption of the National Seismic Hazard Model.
Thank you, Bob. Let me share my screen. Hi, everyone. I hope that you're doing well. Will you let me know if you can see my screen?
Looks great.
Great, thank you. So thanks for that introduction, Bob. I'm Sanaz Rezaeian, and I'm a research structural engineer at the USGS in Colorado. I'm going to talk very quickly today about the building code adoption of the 2023 National Seismic Hazard Model, or NSHM for short, and tell you guys how we developed the design ground motion maps that you see here on this slide, and things like seismic design category and other design parameters. If you attended our last meeting last week, the first set of the webinars, you probably heard the details of the National Seismic Hazard Model. So I'm going to go over this very quickly just to refresh your memory. This update, there you go. This update is a 50 state update. It means that we have updated the hazard model for the entire conterminous US as well as Hawaii and Alaska. And if you guys go to the Earthquake Spectra, a special collection of all these papers that the link is in the chat for you, you can see that the first paper is by Peterson and others. That's an overview paper that will go over the details and summary of all the other supporting papers. People our speakers last time gave you a lot of detail about the process, but I want to remind everyone that this development of the National Seismic Hazard Model goes through an extensive review process. We started this particular cycle by checking with our steering committee, who discussed in detail with us what topics should be included and what should be held back for future research. We went through various review panels for the source models and for the ground motion models. We had regional panels for Alaska, Hawaii, and other parts of the conterminous US, as well as a public review comment and our own internal USGS review process. After all of these, each one of these papers were reviewed just like any other journal paper gets reviewed. And we also ran this by our Building Seismic Safety Council engineers that I will tell you a little more about in the upcoming slides. So just a refresher for everyone, there were a lot of important updates in this 2023 NSHM, but three of the major ones were incorporation of the earthquake rupture forecast or ERF model in the Western US, and NGA subduction ground motion models that were implemented in the Pacific Northwest, and a lot of improvements and new basin boundaries that were added for deep sedimentary basin effects. The central and eastern US also had a lot of updates that I just don't have time to go over, but I invite you guys to read these papers. Longest story short, what I'm going to end up with my presentation is that this National Seismic Hazard Model for conterminous US, part of it has already been adopted into the 2026 NEHR provisions, with a caveat that it should be in a combination with a change to the MCER ground motion, and I will explain that a little more. So what you guys are looking at here is the process of USGS hazard models being adopted into building codes, as Bob Pekelnicky also summarized for you. So traditionally, this has happened. There's no guarantee that the hazard models do get adopted in every single one of these building codes, but this has been happening since 1996 hazard model of the USGS. The latest model, 2023, has been adopted into 2026 NEHR provisions. And when we say adopting, we mean that we are taking the hazard curves that are the main outputs of the USGS hazard models and apply the site-specific procedures of Chapter 21 in the NEHR provisions that are determined by the Building Seismic Safety Council Provisions Update Committee. And these things can include a bunch of complicated processes such as risk-targeted calculations, addition of maximum direction factors, deterministic capping, perhaps being added on site amplifications to give the engineers what they know as design ground motions, or MCER, which is the maximum considered earthquake risk-targeted in the past few cycles. As I mentioned, the 2026 NEHR provisions have already started. This process actually started in 2022. We have to go through a series of processes before the hazard models are adopted into building codes. And us, our group, we serve as USGS liaisons to the engineers of the BSSC PUC. We have to run these proposals through an issue team, then through the Provisions Update Committee or PUC and professional organizations. Very recently, in December of 2024, the new hazard model for conterminous US was accepted and passed all these processes. We still have quite a bit of work left to do, and that includes adoption of Hawaii and Alaska parts of the model, producing high-resolution maps, developing data releases, web services, and educational material. Usually, when the hazard models get adopted by the seismic provisions in NEHRP, they go into ASCE 7 standards. For those of you who are not familiar with this, ASCE 7 standards includes all sort of loading. One of them is the seismic loading, and they usually refer to the NEHRP provisions, but that's not a necessary step. They could deviate from NEHRP provisions. The process of adopting the hazard models 2023 into ASCE 7 2028 started in 2024 for us. There are also a lot of steps to go through with this committee that includes passing it through a task committee, seismic subcommittee, main committee, and member organizations. We are in the middle of this process, so I can't tell you exactly what ASC 728 is going to adopt, but I can tell you that we have passed this seismic subcommittee step at this point, and we might change the definitions of MCER for ASC 728. Let me go back again. Assuming that the maps get adopted into ASC 7, they usually go into international building codes. And the cycle for that would be 2030, which is when the local jurisdictions will pick up the hazard models and start enforcing them. I did mention these issue teams at the PUC for NIHR provisions to you guys. The issue team that we have been working on is issue team number 3. It involves a lot of ground motions and geotechnical issues, which in addition to adoption of the 2023 USGS National Seismic Hazard Model, it includes 8 other proposals and sub-issues. Some of them we will talk about today. One of them deals with replacing the deterministic capping, and Nico will go over the details of that for you, and that will result in MCER definitions changing. Another one is on the coefaction targeted PGA that Andrew will give you more details about. We have also several proposals that change the site-specific site response procedures of Chapter 21.1 that John Stewart has taken on. We will have some proposals on vertical ground motion updates, and the TL parameter, if you're familiar with it, that's a long period parameter in the response spectrum, is also changing for conterminous US and Hawaii. We might have another set of proposals because some people have approached us during this process asking for more educational material. Something like a part 3 resource paper is being worked on to give people who are interested more details and backgrounds on MCR definitions, the history of it, what they look like for all other sites in the US. So let's go back to the hazard model. The speakers of the last webinar explained some of these things to you guys. We basically compare our new hazard models to the previous one every time that we develop these kind of models by making ratio and difference maps. So what I'm showing to you guys in these 3 ratio maps is the ratios between the new hazard model 2023 to our old one 2018. Although some people like to talk about ground motions going up or down in one update, that's not necessarily the case. They can go up or down depending on what period, what site class you're looking at, and what level of hazard you're looking at. And the 3 figures that I'm showing to you, they're all for different combinations of these parameters. So the way that we summarize all the changes for our engineering users is to look at MCER values, and we calculate them for a set of test sites that represent the entire US. From these test sites, you might recognize these red triangles are some of them that have been in the NIHR provisions from the past cycles. These are the 34 cities that are usually in the more populated areas. What we do with these sites is to look at the scatter plots and try to compare the MCER from the last cycle 2018 to the new cycle 2023 in this case. We want to make sure that a group of data from the same location are increasing or decreasing for the reasons that we thought. For example, in Southern California, could it be because we changed the ERF model? In Pacific Northwest, could it be because we changed the NGS subduction ground motion models? And do we expect them to go up or down as a group? In general, in this cycle, we see some increases in the central and eastern US. And these differences were discussed in the last webinar, and I'd be happy to answer any additional questions to you. And we also look at outliers and try to make sense of whether these outliers are reasonably going up or down. In this one particular case, I wanted to focus on the San Jose data. At 0.2 second, the ground motion is going to go up, but at 1 second, it's going to go up a lot more. So we look at these kind of situations and break down the changes in the hazard. What you're looking at in this example map is San Jose at this red dot with a lot of faults that's surrounding it. And what happens in this case is that the faults haven't changed too much, although we have had better approximations because of ERF model. So we break this down and look at the table. For example, at this location, we see that from 2018 to 2023, our ground motions probabilistically don't change that much. They've just been refined and they are a bit more accurate in the representation. What we found is that deterministic ground motions change quite a bit, because now by changing all the parameters a little bit, we are changing the controlling faults for deterministic ground motions. For example, in this case, we are going from Calaveras Fault to Silver Creek Fault, and each one can be a different fault controlling at different periods. So for example, at 1 second, this particular location was controlled by the deterministic lower limit, and now it's going to be controlled by probabilistic ground motion because deterministic ground motion went up way too much. So we are looking at a 41% increase. So this kind of analysis brought us to look at probabilistic and deterministic ground motions separately. For example, in the left-hand side figure, you can see that, yes, there are changes in the probabilistic ground motions that we are looking at, but they are a little more stable, versus deterministic ground motions change drastically with any changes that happen to the hazard model. Particularly the locations that are controlled by these artificially assigned lower limits, they go up a lot. So what you guys are looking at in this slide is our actual proposal to 2026 NEHR provisions. On the left-hand side, you're seeing that we changed the hazard model to 2023 NSHM, but we didn't change the definition of MCER. It is still 1% risk-targeted spectral acceleration that was deterministically capped. And we were just proposing that, hey, we know that there is a better hazard model. Let's use that and change the ground motions. This is how they would affect SMS values. This is short period ground motion parameter. In the process, PUC asked us to revise this proposal and go with a new definition to MCER, which removes deterministic cap and reduces the increases the risk target from 1 to 1.5% for all locations and all periods. So what you guys are looking at is the SMS changes from ASCE 722 to 2026 NEHR provisions that was actually adopted into 2026 NEHR provisions. These changes the ground motions for larger intensity ground motions, up and down, the average almost doesn't change, but it lowers the ground motions at lower intensity ground motions. Things are a little different for SM1. Again, what you see in the left-hand side only changes the hazard model. It wasn't accepted. On the right-hand side, we combined that with the new definition of MCER, and that's the one that was accepted. And we are looking at the long period ground motion here. In summary, the 2023 National Seismic Hazard Model is published now, and you can access it through the link that's in the chat. It has important updates, including earthquake rupture forecast model in the Western US, and subduction ground motion models in the Pacific Northwest, improvements to the deep basin effects, and many other improvements. The 2026 NEHR provisions has adopted this hazard model with a new definition to MCER. The proposals for ASCE 728 are ongoing. That could be different from 2026 NEHR provisions. And if it's accepted, then they would be proposed for the 2030 IBC and IRC codes. With that, I'm going to close this presentation and invite Nico Luco to talk about the deterministic ground motion and the proposal that I mentioned to you guys. Nico, are you online?
Yes, and hopefully you can hear me and
Yes.
see my slides. Okay, great. Thank you, Sanaz. Just want to thank you, EERI, again. Thank you, Bob, for moderating this. Also, thanks to Mark Peterson of USGS. He did a lot of work into working with the EERI to organize this, and he recently retired early, and that's why we don't have him today. So I'm going to talk, as Sanaz mentioned, really about the procedures for deriving the design ground motions from the USGS National Seismic Hazard Model. What I'll present is really a close collaboration with Deborah Murphy from Slate Geotechnical and Sylvia Mazzoni, and we benefited from a lot of discussions with the issue team number 3 that Sanaz mentioned, as well as the provisions update committee of BSSC. Okay, quick outline. So I'm going to give some background, especially for those not familiar, remind people about the deterministic capping of the risk targeted maximum considered earthquake response spectra that's in ASC 722. And similar things were in prior versions. Talk about issues with deterministic capping. Talk about proposed replacement of deterministic capping with increased target risk or risks of collapse. As Sanaz mentioned, one thing has been accepted for the NEHR provisions, so I'll show that. And then example inputs of proposed replacement, MC sub R response spectra with some justifications, and then close just with the status of these and related proposed changes. Okay, so I'm going to go through this pretty quickly. ASC 722, really the definition of MC sub R response spectra is in the site-specific chapter, chapter 21. As you see here, that chapter has a section that defines probabilistic ground motions, the risk-targeted ones, deterministic ground motions, and then it says that the MC sub R ground motion should be the lesser of these probabilistic and deterministic ground motions. To show a flow chart of the process, I'll just go through very quickly. First, we calculate probabilistic risk-targeted response spectra, and then we compare that to this DLL, this deterministic lower limit that's now defined for a whole range of spectral periods in ASC 722. If we're above that lower limit, we go and calculate deterministic ground motions, 84th percentile ground motions, and then again with the lower limit on the deterministic values, we come up with our risk targeted S sub AM values. Right? So don't want to spend too much time on this, but that's a general flow chart. To show one example for a San Jose site, in red here, you see the risk targeted spectrum that we calculate. First, we compare it with the deterministic lower limit spectrum in green. It's above that. And so then we go into the process of calculating the deterministic 84th percentile ground motions in blue. And then we take the lesser of the probabilistic and deterministic subject to that deterministic lower limit in green there. And so one thing you see here is this particular example, what governs is changing from the deterministic lower limit in green to the 84th percentile and blue to the probabilistic in red. And that's something that really was more obvious once we went to ASC 722, and is part of what's kind of prompting a revisiting of deterministic capping. Okay, so talk about issues with deterministic capping. We've done hour-long talks on this, so we'll just be able to summarize, but welcome questions at the end. There are issues identified in 2020 NEHR provisions resource paper. I'll show that in an associated earthquake spectral paper. Large and irregular increases of risk of collapse. I'll show a couple figures for that quickly. The basis of the deterministic lower limit, it was based on magnitude 8 at 12.5 kilometers using NJ West ground motion models. And yet we were trying to apply that everywhere across the US and territories. And then deterministic computations, really this last part is just that, deterministic ground motions are defined in chapter 21 of NSC 722, but there are different ways to interpret what is written there in contrast to the risk targeted specification of the probabilistic ground motions. All right, so the near provisions, again, people might be familiar. There's a part 3 that has resource papers, and there's a paper there on risk-based alternatives to deterministic ground motion CABs. That resource paper actually got turned into an earthquake spectra paper that you see on the left here, and that paper shows some figures and makes some references to, I guess, an EERI co-organized the World Conference in 2017, a paper there. All right, so showing the first figure with the issues in deterministic capping. This is a map that shows you the risk of collapse that results from MC sub R ground motions. This map in particular is for 0.2 second inside class D. Right? So most of this map is green, mostly boring, and that's a 1% in 50-year risk of collapse that results from MC sub R ground motions, because that's what the probabilistic ground motions were targeting, 1% in 50-year collapse risk. Right? So in places that are not green, right, it's because we have some deterministic capping to various levels, sometimes a lot of deterministic capping. And when you deterministically cap a ground motion that was supposed to give you 1% in 50-year collapse risk, you're going to end up with higher risk because you're reducing the ground motions you designed for. And as you can see, there's some places, 0.5% of the population where the risk of collapse gets up into the highest bit of 4 to even 13% in 50-year collapse risk. Right? So wide range in collapse risk that result. You can't ask yourself, is it a problem that we've got higher risk along San Andreas? And so this next figure is intended to discuss that. So this figure shows every point on here is just a point from the previous map. On the x-axis, we're just showing the risk-targeted ground motion value. It's sort of a measure of how much hazard there is at each location. And then we're showing the collapse probabilities at collapse risk in 50-year on the y-axis. So at lower ground motion or lower hazard areas, the collapse risk that results is 1% in 50 years. But as you see, it gets bigger in deterministically capped areas, but it gets bigger in a very unconstrained way. And so one example right here is Sanaz and Santa Rosa are both pretty high hazard locations, but one's ending up with about 1% in 50-year risk, and the other is above 6% in 50-year risk. Right. There's a reason for proposal that talks about this more that I'm happy to share, but also will turn into probably an earthquake spectrum. All right, proposed replacement of deterministic capping. So just a few ways to describe this visually quickly. I showed this flow chart of what you have to do for deterministic capping. The idea was just get rid of everything below calculating probabilistic risk targeted ground motions and just do that with a different target risk. And what's been accepted for the 2026 EERI provision is 1.5% in 50-year target risk. If you look at the chapter 21 in the section that defines the risk targeted ground motions, really see it really just takes out the deterministic ground motions part, and then you can barely see it, but it really just changes 1% in 50-year probability of collapse or risk to 1.5%. Right? So pretty basic change. This is another way to illustrate this, right? So same plot as before, showing the resulting collapse probability in 50 years or the risk that results from the MC sub R ground motions as a function of hazard level. What we're doing with this uniform 1.5% 50-year target risk of collapse is essentially collapsing all these black points onto this red line. Right? So you see some places that the target risk is going up compared to what we had before. You know, some places the target risk is much lower than the risk that was resulting from MC sub R ground motions. And this is where I'll just mention what Sanaz touched on, which is there has been discussion, and there continues to be a discussion about potentially increasing the target risk only at higher hazard locations. And that would be this green line where it's left at 1% in 50 years, low hazard, goes up to maybe 1.5 or 2% in high hazard, and then there's a transition. So that's still under consideration. All right, example impacts of the proposed replacement of deterministic capping. All right, so start with just this plot that's for S of MS. So this is showing the impact just of replacing deterministic capping with a 1.5% 50-year target risk. So this is S of MS, or the short period spectral values from ASC 722 that have deterministic capping on the horizontal axis, and on the vertical axis, the ground motion that results from the 1.5% 50-year target risk. So a couple things you can notice: that lower hazard areas, the bottom left, right? You're seeing reductions 15 to 20%. Charleston, it's up to 22%. And this is again because in lower hazard areas, ASC 722 was using a 1% of 50-year target risk. Now we're up to 1.5% on 50 years. At higher hazard areas, on average, we're not seeing much of a change, not much outside the plus or minus 15 to 20% range, except for San Jose. That goes up a lot. And that's because, as we saw before, right now there's a lot of deterministic capping at San Jose. That makes effectively the risk there very high, above 6% in 50 years. And so using 1.5% in 50 years still gives you a bigger ground motion than what we had before. And same kind of plot for 1 second. The only thing I'll point out is that at 1 second, there's not as much deterministic capping in ASC 722. And so this 1.5% 50-year target risk is giving us a lot of 15 to 20% decreases. All right, and then a quick plot. This is the same plot, except now instead of using the previous plot, you use the 2018 USGS hazards model for both cases. Now we're saying let's look at ASC 722 with the change to 1.5% 50-year target risk and the 2023 USGS hazard model. So the change of both of those things, the impacts of those things. And I'll toggle back and forth, and you can kind of see with the 2023 USGS hazard model, see a lot of points kind of drift upwards, which actually gets a lot of them closer to the 1-to-1 line, or the plus or minus 15 to 20% range. So San Jose, right, is a big still outlier, big increase, and Charleston is a bigger decrease. So I'll quickly provide some justifications here. San Jose, this increase of 41% is justified by the fact that the amount of deterministic capping San Jose in short spectral periods, like a 50% decrease, was by far the largest amount in our example cities. The ground motion return period of the deterministically capped MC-SPAR ground motions from ASC 722 was only 300 years for MC-SPAR at a spectral period of 0.2 seconds in site class D. Sanaz showed you some of this. If you just updated to the 2023 USGS hazard model with deterministic capping, you'd still get an increase in San Jose. And that's really just because of which faults end up governing in the deterministic capping procedures. And then this is another thing that the group looked at. There were some people thinking about, well, how does this compare to uniform hazard 500-year ground motions divided by our design 2/3 factor? That would also tell you that ground motions at San Jose should increase. And then Charleston, I'll go through this very, very quickly. So Charleston, things are decreasing, but we do need to remember a little bit of the history. In 1996, the USGS had estimated the return period of large Charleston and New Madrid earthquakes as 650 and 1,000 years. In 1997, this Project 97 selected a ground motion period that was about 2,500 years, thinking something that was more than twice the return period of the earthquakes, but then deterministically capped that in high hazard areas. Then in 2002, USGS improved the New Madrid seismic zone earthquake return period from 1,000 years to 500 years, and it's been that ever since, but we really haven't gone back and revisited the 2,500-year return period. That 2,500-year return period in 2007 was really the basis for Project 07, selecting a target risk of collapse that's 1% in 50 years, at least across the Western US. So now one way of thinking about this is that if you think about the improved pneumatic seismic zone earthquake return period, and you also recognize that when we were deterministically capping, we were effectively looking at lower return periods or higher target risks, that leads us to a higher target risk, like 1.5%, 50 years being reasonable. All right, so I showed just some few example results. Sylvia Mazzoni has created a really fun website and with lots of information. We'll put the link to this in the chat, but you can look at all kinds of results there. And then I'll just close with the status of the proposed changes. So replacement of the MCSVAR deterministic capping with a 1.5% 50-year target risk, it has been accepted for the 2026 EERI provisions. So you'll see that. Analogously, for geotechs on the call, right, the MC sub G, PGA sub M deterministic capping that's in ASC 722, there's a proposal to replace that deterministic capping with just a 3% 50-year ground motion exceedance probability uniform hazard. And that's almost been accepted. It's in the very last stage of resolving comments from BSSE professional organizations. As Sanaz mentioned, both these changes are now being validated for the 2028 ASC 7 standard. A couple just adjacent projects. For the NEER provisions, there is an appendix being developed for functional recovery. And that proposal in terms of ground motion is using a uniform 10% 50-year target risk for functional recovery ground motions. And then as you will hear from Andrew, and so this will be the segue, there's a uniform 2.5% 50-year liquefaction probability for PJL that's been accepted for 2026 NEER provisions. So with that, I will turn it over to Andrew, who will talk about PJL, if not other things, and look forward to the discussion at the end.
Thanks, Nico. I'm going to steal the screen from you, or if you could.
I can stop share.
Okay, thanks. All right. Hopefully, folks, this will take a second, can see the full screen.
Now you can.
Okay, cool. So there's a little delay. I'll try to account for that. Yeah, thanks. Thanks, Nico, for the intro, for the nice segue. Thanks to EERI for holding this webinar, and thanks to Bob Pekelnicky for emceeing. So I'm going to shift gears very, very slightly, talk about how the 2023 NSHM and really seismic hazard models in general can not only be used, as Nico showed earlier, to advance kind of risk-based design guidelines, but analogously, we can do the same on the geohazards design guideline side. So the way I'll kind of walk through this is talk about what we currently are doing and our current MCE sub G PGAM that we use for geohazards, and maybe a brief historical perspective and some of the limitations that have kind of evolved from the use of the MCE PGA sub M. I'll use that as sort of motivation to discuss a proposed and developed proposal over this cycle to introduce a liquefaction targeted PGA sub L that could be used for design against liquefaction hazards. Some of the mechanics I will walk through was our BSSC provisions update committee working group, sort of what our group makeup and the tasks that we undertook to put this proposal together. And some of the main tasks and the big themes that I'll talk about is sort of how we developed a good concept of what the current acceptable probability of liquefaction that is implied by our current design standards is, and sort of how we use that to calibrate a probabilistic liquefaction targeted design basis, which in this case came in the form of a specified acceptable probability of liquefaction, and then kind of the how we might derive the loading parameter, the design parameter PGA sub L, to meet that design basis, and how is expected to impact current design relative to the PGA sub M. So this is my kind of personal reading of the historical perspective on how we've developed seismic parameters for structural design, as well as seismic parameters for geohazards. And to do that, I kind of went all the way back to 1978. And I'll just say this is my, again, I was not around in 1978 or really for quite some time during this development. And so this is sort of my interpretation of sort of how we've evolved to get to where we are today. So as Bob mentioned on his introductory slides, the ATC 306 tentative provisions provided us with seismic zone maps. Those were based approximately on 10% 50-year peak ground acceleration maps from the USGS, and those were used through the 1994 NEHR provisions. On the geohazard side, we basically said, let's use the same PGA. We're just going to call it A max for use in liquefaction factor of safety calculations. And those values, again, were taken directly from those same seismic zone maps. In 1997 NEHR provisions, there was a shift to 2/3 of the newly defined MCE. That's the 2% 50-year probability of exceedance. And this, I'll just broadly say, was underpinned by a desire for more consistent margins of safety against collapse, particularly under extreme ground shaking levels. And that also included adoption of the deterministic cap in coastal California. On the geohazard side, there was this corresponding shift to the MCE, that 2% 50-year. And I think there was maybe a 1 or 2 cycle stretch where it was unclear whether that 2/3 reduction should be taken. At a certain stage, there was clarification that you really shouldn't be taking a 2/3 reduction for geohazards. So that is to say, we kind of continue to use the MCE with no 2/3 reduction. And then in the 2009 NEHR provisions on the structural design side, there was some acknowledgement that this collapse capacity, this margin of safety, was highly uncertain. And that's where sort of the motivation for the MCER risk target came from, to account for that collapse fragility. And then kind of the 2009 NEHR provisions stayed the course for geohazards, continue to use the MCE, and have continued to do so through the present day. And I kind of provide this perspective mainly to highlight some differences with how these two different parameters have been developed. On the structural design side, this has kind of all been about targeting life safety related performance objectives. And they've done so by considering the capacity against collapse, as well as the inherent uncertainties. And so that's sort of driven and underpinned structural design really for decades now. For geohazards, we've sort of just developed our parameters to match for historically the same uniform hazard levels that were used in structural design, but then structural design moved away from uniform hazard to risk targeted. And geohazards didn't really do that. We basically didn't include any sort of capacity against geohazards. And so at present day, it's kind of unclear what performance objective we're targeting with our current geohazards provisions. It doesn't really appear to be life safety or collapse prevention. And it's sort of this parameter that's been along for the ride for several decades now. And so maybe there's time to revisit and see if we can refine this a little bit, at least take a step forward. And this particular working group decided to do it through the lens of liquefaction hazard analysis. So we have this MCEG PGA sub M. It's deterministically capped in some places. It's 2% 50 in others. The MCE presents a single point on our PGA hazard curve, and it also requires a single representative magnitude to account for duration effects. It does not account for uncertainties in liquefaction triggering, that kind of concept of capacity against liquefaction hazard triggering or consequences. And as a result, thanks to previous studies, initially from Kramer and Mayfield, and then later through myself and Steve Kramer, really results in these inconsistent, uncontrolled design levels with respect to liquefaction triggering. And this may look a little bit like, quite a lot like what Nico presented on the previous slide, with risk levels, particularly in deterministically capped areas. And And so the goal here was to develop, like I said, a liquefaction analog to collapse risk targeted ground motions. We are proposing a liquefaction targeted MCE sub L, peak ground acceleration, this is PGA sub L, that's intended to approximate a fully probabilistic liquefaction hazard analysis. I will say this is not the first time that this sort of procedure has been proposed. There's been several papers over the last couple of decades almost that have aimed to get probabilistic concepts into seismic design. The goal here is to capture really a lot more information that we get from national seismic hazard models than just a single return period PGA. This is asking us to take the full PGA hazard curve as well as duration effects from all of the contributing magnitudes, which we can also get from NSHM output. We're also including estimates of the uncertainties in liquefaction triggering, with the underlying goal here to get a more consistent liquefaction targeted design basis. And we're doing this through a maximum acceptable probability of liquefaction triggering, above which consequences and potential considerations of mitigation against liquefaction hazards need to be explored. So just to sort of borrow from Sanaz's earlier slide, there was a bunch of BSSC sub-issue teams, and we are sub-issue number 3. This is the team that was working through liquefaction targeted PGAL. This is our group. It was co-led by myself and Steve Kramer, and included a range of really valuable contributors, both in practice and in academia. Our working group task, we sort of took this from cradle to grave. We sort of settled on a rigorous method for how we might compute the design PGA sub L, be able to provide it to practitioners really with the same, delivering it through the same parameters that are currently provided through USGS geodatabases and also through the ASCE7 tool that Bob alluded to earlier. A really critical step was characterizing, again, those current effective liquefaction design levels so that we could then calibrate our target design levels in order to sort of minimize impacts on the whole. And then, of course, developing provisions update language. Okay, so the reason, again, like I said earlier, is we wanted to keep impacts on design levels relatively minimal. And so we sort of thought that at least the first step would be to use probabilistic analyses to constrain what our current implied probabilistic design levels are. And this was a very large scale evaluation of current design levels using ASCE7 ground motions and a bunch of liquefaction triggering models that are commonly used in practice. We looked at 160 geographic locations. This map is the same map as what Sanaz showed on her last slide. We're just now scaling the markers for population, and that'll come in handy later. A wide range of soil conditions and a wide range of just modeling conditions that people tend to use in their approaches to liquefaction hazard analysis in practice. And then we looked at a lot of different ways that we might average those effective design levels across all of these study conditions. And so again, what we're asking really deep down is, what is the maximum acceptable liquefaction probability that engineers are implicitly designing to? So mentioned earlier, we don't have a liquefaction targeted performance objective currently in the MCEG, but that doesn't mean we don't have an implied one. And so what we wanted to do was get a sense of that and also see how it varied from region to region. And so again, this is kind of similar to the plots that Nico was showing on the last slide. These are showing on the y-axis our effective 50-year factor of safety probability as a good stand-in for our effective liquefaction probability. We've split up these markers by region, and then on the x-axis, we're plotting them with respect to essentially seismic hazard level, the 2475-year PGA for site class D. The darker outlined markers that you see up on the right side of the plot are sites that we've indicated are generally controlled by deterministic considerations. And so we can kind of start to get a sense of how these vary from region to region. We've got about a 2 to 3% and 50-year probability in the central and eastern US, about 2%, give or take, in the Intermountain West, 1.5 to 2% in 50 in the Pacific Northwest, particularly along the coast where Cascadia tends to dominate the hazard. And then we get to our sites in the Western US that are deterministically capped, largely in California, with a few sites in Washington as well as I think Nevada. And that's where things really start to become problematic. There's a very wide variation due to deterministic capping, and we see ranges from about 3 to nearly 15% in 50 years. And the implication here, similar to the risk targeting issue that Nico outlined, is that in this area, our liquefaction design standards are much looser. They're far less stringent than they are throughout the rest of the United States. And this is, again, kind of the same information, but this is where we started to bring in some potential averages from region to region. We include columns for allowing us to weight these averages by population as well as seismic hazard. And effectively what we arrived at was this 2.5% in 50-year liquefaction return or probability, or a return period of just under 2,000 years as our liquefaction design basis. And this is again informed by our current implied design levels. So going from there, that's our target MCE level that we proposed for this update cycle. And we're just sort of walking through how we were able to map PGAL at a particular site and particular site class for that level. And so on the left-hand side here, or I guess I'll start by saying, we do this for a reference soil condition. And the reason we do that, we're able to do that is there's some supporting research that PGA sub L is actually largely insensitive to soil conditions. And so we don't need to present PGA sub Ls for all depths, all stress conditions, all relative densities. So on the left side of the figure is essentially what's going on under the hood. It's a probabilistic liquefaction hazard assessment. It produces factor of safety hazard curves at the reference condition. And this is how we integrate the full NSHM hazard curve with the liquefaction fragilities that we've selected. We've used 4 different triggering models with varying weights to sort of capture both aleatory variability and epistemic uncertainty in liquefaction triggering. And we select our target return period. We pick out our reference factor of safety. And then on the right-hand side is our deterministic analog. And that's where we can relate our design peak ground acceleration, PGAL, that's magnitude adjusted, to that factor of safety and compute the value required to obtain or at least approximate the hazard consistent return period on the left-hand side. You can repeat this for other site classes and other grid points. And again, produce that same seismic design geodatabase. I'll just quickly walk through the design impacts. These are one-to-one plots showing the proposed NEHR provisions PGA sub L with the ASCE 722 PGA sub M. That's notably is magnitude scaled so that we have a one-to-one comparison. This is for default site class and site class E. I've also provided this in tabular form on a region by region basis, showing the changes in PGA within a given region and the ranges of those increases or decreases, as well as the number of sites where we expect changes to be greater or less than 20% and also 50%. And there's a few different sources of changes here. The biggest one, similar to what Nico had mentioned earlier, is the removal of deterministic caps, largely in California and very pronounced at site class E, that are driving up these PGAs in this region. We're also seeing increases in PGA at lower hazard Central and Eastern US sites. This is actually more driven by the 2023 NSHM update. So this is a different source of change that has really nothing to do with the shift to an MCE sub L design basis. And then finally, sort of the core change that we're proposing is effectively an increase in the acceptable design levels from about 2% in the Pacific Northwest and Intermountain West to that 2.5%. That's a loosening or a less stringent design level that's leading to a corresponding reduction in the design loads. Okay, I think I'm pretty much out of time here. So what I'll just close with saying is the overarching goal here, and in a lot of our risk-based or demand-based provisions, is that we should be able to go beyond uniform hazard design loads when possible. We've got all this really good information embedded within our national seismic hazard models. And so rather than picking a single return period on a hazard curve, we can integrate kind of the full hazard data, that full space, with appropriate fragility functions, whether those are for collapse or for ground failure, or for whatever limit state that we care about, to derive either risk-based or demand-informed design load parameters. And that's what we've done here with this magnitude-adjusted MCEL-PGA. It's a parameter that's not perfect by any stretch. It still doesn't relate to collapse risk or any specific performance state, but we do feel that it's more appropriate for liquefaction hazard assessment. Again, it incorporates the full hazard curve from all contributing magnitudes. It doesn't require users to select a single magnitude. It includes uncertainties in liquefaction triggering estimation. We are anchoring it to a 2.5% and 50-year probability of triggering, and that is calibrated to our acceptable liquefaction probabilities that are implied by current ground motion levels. Just to give an update, it is pretty much on track to be adopted in the 2026 provisions, and it's currently balloting at the ASC 728 Technical Committee 1 level. So I have a question slide, but I will leave, I guess, questions towards the end. And I thanks for your time. And what I'll do now, I guess, is introduce Kishore Jaiswal. He's project lead within our Earthquake Hazards Program, Engineering and Risk Project Group. And he'll be presenting on earthquake loss estimates using the updated 2023 model.
Andrew, can you hear me?
Yes, yes, I can.
And can you see my full screen?
Yep.
Awesome. Thank you for that, Andrew. Hi everyone. My name is Kishore Jaiswal. Previous speakers have done a great job in showcasing how the National Seismic Hazard Model has been used for building code applications, and this presentation is about how the hazard models can be used for seismic risk estimates. And I'm going to, let me see if I can minimize the screen. So in the next several minutes, I'm going to give a quick view of seismic risk estimation procedure, as well as some initial assessments based on the 2023 model. We haven't completed the 2023 risk estimates yet based on 2023 NSHM. However, we have recently published a joint USGS FEMA study, which on the right-hand side, there is a front page cover of that report, which was released in 2023. This estimate basically provides a nationwide view of seismic risk in the United States based on 2018 USGS hazard model. And this work, like I said, is done in collaboration with FEMA. We appreciate that partnership very much. The researchers from FEMA, especially Jesse Rosal, Casey, Mike Tong, and many others, including FEMA contractors, contribute to that work. So what I'm going to do is I'm going to talk about the evolving risk. But before I do that, I must acknowledge that some of the information I'm presenting here is preliminary and it's subject to revision. And again, this is done basically to communicate the best science available out there for people's consideration. I'm going to focus, yes.
Sorry, Kishore, sorry to interrupt. There's just a request for you to turn your camera on, if you don't mind.
Is it not on?
No.
Well,
We see your screen, but we don't see you on the video.
Okay. I hope you can see me now.
Yes, that's great.
Okay, wonderful. Okay, so in the next few minutes, I'm going to talk quickly about how USGS hazard model, the mean hazard has changed over the different cycles, what those changes mean in terms of how many people are exposed to different hazard levels, how many buildings, how much economic exposure is out there, and then give a quick view of what does the USGS 2023 model means in terms of seismic risk in the United States. Okay. So the data and the models that I'm using are pretty much available publicly. So you can go to the USGS hazard webpage where you can find the hazard data for different versions of the different cycles of these models. And I'm going to use those for performing some analysis of how hazard has changed over the years. So this slide shows how the hazard has changed between 2018 and 2023 in terms of modified Mercalli intensity. So we take the PGN's 1 second spectrum, response spectrum hazard value for different hazard threshold from starting from top left is 50% in 50 years, which is roughly 74 year of return period, to all the way to the bottom is 2% in 50 years, which represents roughly 2,500 year return period. So something that you can expect in your lifetime, which is on the top side, and the bottom is something which is very rare, but it can happen and potentially can cause significant damage or destructions. So you can see that the hazard has changed compared to the previous version of the hazard model. The area on the red zone shown here shows that hazard has increased. The area in the blue shows the hazard has decreased by at least 1 or 2 MMI intensity unit. So these maps are useful to show like a big picture view of what is going on in terms of changes in hazard. But let's look in terms of how much area has been changed. So this plot essentially shows the last 6 cycles of the USGS hazard model in terms of mean hazard, all converted into a representative MMI value based on 2% in 50 year. And the bar chart essentially shows that if you focus on just the 2023, the purple bar shows that you have more land area now exposed to higher intensity, the damaging intensity shaking, MMI 7 and above, compared to any of the previous cycles. So what it means is that we have more land mass is now seeing those higher ground shaking values. How does it compare to the population in terms of? So this slide essentially, I don't want you to read through all the numbers, but essentially we're taking the latest population data from Landscan 2023 version and trying to use the same population data for all the hazard cycles, 6 cycles. And the numbers essentially show to you that compared to any of the previous cycles, we have more people now exposed to damaging shaking. For example, if you look at 10% in 50 year, we have like 5.5 million more people are at that level of shaking compared to the previous cycle. Similarly, if you look at the slightly rare ground motions, 2% in 50 year, you can see that 47 million people are now in the same level of shaking compared to the previous hazard model. In terms of total residential building counts, again, we see the same trend here. We have definitely more structures now are located in the high hazard regions in the country. So definitely significant increase in terms of number of structures at those levels of shaking. 15 million residential buildings are exposed to that level of shaking of MMI 7, which could cause damage in the structures. This slide basically shows the same analysis, but it's in terms of economic exposure. Again, the numbers are in trillions of dollars. So we have, again, the same trend. We have higher economic exposure. Now, this economic exposure is based on the total building stock value. So that includes residential, commercial, industrial buildings at each location. And this, again, the trend is similar. We have more economic exposure now is at that level of shaking based on the new 2023 hazard models. Now for seismic risk assessment, we are pretty much using the consensus-based hazard loss methodology to perform risk assessment, which is fairly documented well in terms of hazard technical manual, as well as research publications from Charlie Kircher and others. So in essence, we use the default hazards building inventory. We map into structural types. We assign appropriate fragility functions, and we perform risk calculations based on USGS hazard models. So as you very well know, the hazard models are basically a probabilistic forecast, long-term forecast. And for risk assessment, we are looking at only certain return periods to perform this analysis throughout the United States. So we are looking at anywhere from 100-year return period to 2,500 return period. We're calculating losses for each return period and then summing up to get an annualized loss. Of course, there are a number of limitations in such analysis, and we acknowledge that in the report. So of course, in the current update, what we did last time, 2023, we did not include the impact coming from the critical infrastructure. We did not also consider the induced seismicity or time-dependent hazard models. But the results essentially gives you a first peek of what is the risk that is associated with earthquakes in the United States, and that comes down to $14.7 billion per year. Now, this is, again, like I mentioned to you, is based on 2018 hazard model, and that was done for all 50 states as well as the US territories. We have done that calculation. This slide just shows that how the annualized losses are basically in terms of where the risk is highest. You can see that California and pretty much West Coast dominates that risk, but that risk is not just focused on West Coast, it is also there in other states, especially the New Madrid seismic zone and other places. This slide essentially gives you a quick assessment of how the risk is changing over time. The FEMA 366 analysis has been done several times in the past, and that just showcases that the risk seems to be increasing quite a bit because we have more people and more infrastructure is at stake at those hazard levels. The new update of 2023 hazard model has also been used right now to perform risk assessment using 2023 NSHM. And we are trying to bring that hazard into the USGS, into the risk assessment, and introducing new code categories for the seismic risk assessment, especially because, like Bob mentioned, the new IBC ERA code adoption has really has significant improvement in terms of not only the hazard, but also how the engineers design those buildings, and that needs to be reflected in terms of the seismic risk associated with those buildings. So the FEMA colleagues have been working with private engineers to develop new code categories here, very high code and severe code, which essentially means that we have a different fragility assigned to those structures, which are especially built with the IBC ERA code. That means they are designed for much higher ground motions, and thus the risk might be much, much lower. And that is being reflected through the modification that is shown here. There are a number of other changes that are introduced in the new inventory exposure model that I don't have time to discuss, but obviously this is work in progress, and some of those things will be discussed as a part of the next release of the FEMA model. This is essentially this slide shows if you use the latest exposure that is built into HAZAS MH 6.1, and we use the 2023 hazard model, we are essentially seeing an increase, a slight decrease in the annualized loss, and that decrease is mainly because of the code changes that we are assigning to the buildings that are being built in the IBC era code construction. For Alaska, we are seeing a significant increase in the risk in terms of annualized loss that are shown here. Keep in mind that if you just don't use the code changes, and if you use the 2023 hazard, the hazard is going much higher. However, because of the modification into the fragility parameters, there is a decrease in California. And in fact, we found that there was a $1.5 billion decrease just because of better code adoption in the country, better building codes. But unfortunately, that is being washed away because of the changes in the hazard that has been introduced in 2023. And again, this is not anything negative. It's just USGS were trying to use the best available science to provide it for risk assessment, and that is what is being done here. So in conclusion, I just presented to you how hazard has changed over different US NSHM cycles. And essentially, we're seeing that we have more people and more buildings being exposed to those damaging shaking levels, which clearly begs the question of, or answer the question of increasing risk in the United States. I also showed you the risk associated with the 2023 NSHM, which talks about that the risk in the country. And very soon, by November, hopefully by November of this year, we'll be providing a new update to risk assessment using the 2023 NSHM. Losses are increasing, as I showed to you, because of the exposure, but also there is a significant decrease in the vulnerability as we are demonstrating use of the latest building codes. And because we are building each year, we roughly replace 1% of the building stock in the country. And in last 25 years, we're talking about almost 25% of the exposure roughly being designed to much higher and stringent code, and thus reflecting that the risk is decreasing essentially because of better building codes and better engineering practices in the country. So with that, I want to conclude, and I want to bring back Bob for moderating the next session. Thank you.
Thank you, Kishore, Andrew, Nico, and Sanaz. That was tremendous. So we have a few minutes to go through the questions that have been put in the question and answer box. So I'm going to ask for those of you who've been enjoying this webinar, if anything has come up and you have not put a question in the question and answer box, now is your time to do so. We're going to try to get through as many questions as possible. So the first question I'm going to direct to Nico, and there's a question regarding Puerto Rico getting the NEHRP ASC 7 and ICC code adoptions. And if you can share when the Puerto Rico seismic hazard model updates will be seen.
All right, thanks, Bob, and thanks, Ricardo, for the question. Ricardo, as you know, we are on track to publish the 2025 USGS National Seismic Hazard Model for Puerto Rico, the U.S. Virgin Islands, by the end of this calendar year. We are also starting to work towards proposing the use of this 2025 Puerto Rico hazard model for the next NEHRP provisions, 2026, ASC 7, 2028, and IBC in 2030. I can see from your comment, right, that you feel in Puerto Rico it's needed more rapidly. So I think the hazard model will be available, and you will have tools to take that hazard model and derive, MC sub R ground motions, for example, from that hazard model. The question you will be faced with is, what procedure do you use to go from the hazard model to MC sub R? Is it what's in ASC 722, what's been approved for the 2026 NEHRP provisions, or if it's something different for ASC 728. So that'll be an important thing for discussion, but the hazard model will be available for you to get the values you need, even before 2030 IPC.
Thank you. Moving on to the next question, I think this might be for Sanaz. What are the differences between the different 2023 map versions, and what is the latest version?
Thanks, Bob. So I think this question is asking about versions that we haven't publicly talked about, but some people are aware that we have been using these V3, V4, V6. I believe V4 was shown in one of my slides, and that's where this question comes from. So in that regard, I want to mention that the version that will be adopted into 2026 NEHRP provisions is going to be the version that Alison Shumway presented in the last webinar. And that means that there is a revision paper that's going to go into earthquake spectra, and it will be amended to this collection. So that's going to be the version. For the people who have heard about these V numbers in the back channels, that's going to be V6. That means that we are incorporating all the latest changes into what will go into the building code. The original publication by Peterson and others, that was V3. And that's just for the people who were aware of these numbers.
Thank you. And then this one is to Andrew. What is the rationale to change the liquefaction evaluation from 2% in 50-year to 3% in 50-year probability of exceedance?
Yeah, I'm happy to tackle this one. I think this was asked at the end of Nico's presentation and before mine. So, okay. So a quick clarification is that the general geohazards PGA, the PGA sub M, is at the same time being revised from 2% to 3%. And at the same time, it's not being used for liquefaction. So the PGA sub L that we're proposing that's passed through the NEHR provisions would essentially remove the PGA sub M for any liquefaction hazard calculation, and then the PGA sub M would still be used for any other geohazards evaluations, such as slope stability calculations. The rationale for that shift from 2 to 3% was effectively because we were dropping the deterministic cap for the MCE sub G PGAM. And so it's a lot of the similar rationale for increasing the risk target from 1 to 1.5% in 50 years. The 2 to 3% seemed like a reasonable compromise in order to sort of even out effects across the entirety of the United States and not penalize areas that are deterministically capped currently too much. So hopefully that answered the question and then also clarified it a little bit.
Okay, thank you. And then this one is going to go to Nico. It seems that there is not only a replacement for the deterministic capping, but it seems the whole spectrum now has a uniform risk of collapse of 1.5% instead of 1%. Is that correct?
Yeah, thanks for the question, Fernando. That is correct. And I'll just mention something, in the short presentation, I was able to show a map that at some locations where we're deterministically capping in ASC 722, the risk of collapse is actually higher than the 1% 50-year target because we are deterministically capping the ground motions. That is also true across spectral periods. In ASC 722, some spectral periods are deterministically capped more than other spectral periods. And this is even true across site classes. Some site classes might be deterministically capped by more or less than other site classes. So there was a variation in the risk, like spatially at location, across period, and across site class. And yes, you're correct, the 1.5% and 50-year target risk, the uniform value now applies to all locations, all spectral periods, all site classes.
Okay. Thank you. There's now a question. This is going to Kishore. Actually, I'm sorry, the question is to Andrew. Is there future plan to have targeted ground motions for landslide risks similar to liquefaction targeted PGA that you presented?
In theory, yes. I think that's a really good question. It's something that was discussed quite a bit this cycle, that we were putting in a lot of work to push forward the probabilistic liquefaction provisions, and that there's clearly will be a need in the future to do the same for landslide. It's just going to require some additional research, either within the USGS, or if external researchers want to tackle this issue following the template, then it's something that the USGS and building code community can certainly support.
Okay. So I'm going to put this to the panel and I'll leave it to you all to jump in first, because I think this is an overarching comment. The ping pong effect of the National Seismic Hazard Modeling Codes is causing a distrust in the National Seismic Hazard Model, in this questioner's opinion. Can you please comment? Now, Nico, if you want to start.
Oh, I'm happy to start. Start out just saying, right, earthquakes, especially big damaging earthquakes in the US, right, don't happen that often, right? So there is a lack of the data that we're really most interested in, and that does lead to uncertainty in our forecasts about earthquake hazard. So, the good news is, right, that we don't have all this data about big earthquakes that have collapsed buildings. Bad news is that makes it harder for us to forecast. And so we do see changes. We have to keep those in the perspective of the uncertainties that are involved in forecasting earthquake hazard. But the other thing I would just say is that there are times in applications of the USGS hazard model where we are using it in such a way that makes us particularly sensitive to those changes in the USGS hazard model. An example of that, a lot of people on this call probably know is seismic design category, right? Seismic design categories can change with a 0.001 G change in ground motion. And that's a very small change that's really beyond the precision that we've got with hazard model giving the uncertainty. So we're doing our best. We try to over time we try to stabilize the hazard model as we get new information, and at the same time we want to make sure the way we're using that hazard model doesn't make us particularly sensitive to the just intrinsic uncertainties in earthquake hazard. Happy if anyone else wants to jump into it.
Maybe I add a comment, Bob?
Yes, please.
So what Nico said, double on that, but I also want to mention that part of the problem is that engineers are using the median ground motion that comes out of this hazard analysis and not the uncertainty. Which is okay, but part of it is because the median is oscillating up and down. Now, we are trying to get away from deterministic ground motions. One reason for that is probabilistic ground motions already have some of the uncertainty in them, and they are in general more stable over time, versus deterministic ground motions are a lot more sensitive to these this guy called it ping pong. Some others have called it yo-yo effects because they go up and down. So just by moving away from deterministic definitions and going into probabilistic definitions, this is going to help the profession as a general to just be more stable, unless, of course, we find something new. We have a new large earthquake, in which case things should change.
Great. Nobody else wants to add. I'll go now to comment to Kishore. For the analysis using HAZUS, can you elaborate on the comment, when the new building code effects are not being used, then the hazard change is much larger? Do you have a quantitative range of how much larger the AEL is?
Well, like I said to you, we're still processing that kind of work. We're still analyzing. We have completed number of states, but your observation is correct. If you just resume the same code category definition that has relied on previously, the annualized risk estimate are significantly going up. However, we know that that was a deficiency in the HAZUS approach of mapping those newer structures into de facto high code category. However, that definition of high code was really based on the UBC era codes, and engineers have been designing buildings in a much more efficient and much more rigorous way, and that needs to be reflected in terms of the true vulnerability that those structures would have in the event of a large earthquake. So that effect is definitely significantly bringing the losses down, just like I mentioned. Again, we are still in the early phase of this analysis, but there was a reduction of $1.5 billion just in California because of just the IBC era code adoption. And this is an important message for the community, that swift adoption of building codes is really critical, because, like I said, each year we build about 1% of the build stock. We just add that new building stock to the current fabric. And thus, if we're designing for more up-to-date seismic codes, that would really influence the potential future risk of those buildings.
Okay, thank you. So I think we're approaching time, so we might be able to hang on for a couple more minutes. The next question is either to Nico or Sanaz. I am wondering if there's any change regarding the question of geometric mean versus maximum direction? Is this something not recommended by seismologists? The commenter, the questioner's understanding is that part of the motivation for using maximum direction was to offset some of the reductions that resulted from the NGA West 1. If the collapse hazard is being revised, is it time to also resolve this discrepancy?
Yes, I can't say that that's in this cycle. A change or revision there is not being proposed. And I would probably describe kind of where things have landed as there's not one answer whether max direction or geomean or median is the right metric. It depends what you're doing with it. And so in fact, for buildings, you know, I think even some of the folks that argue with max direction say for buildings, it's one of those cases where max direction can make more sense compared to, for example, bridges, where we might have very clear and different behavior in orthogonal directions. So yeah, I think that the discussion's gotten more nuanced and it's not leading to a change for the NEHR provisions.
Okay. With that, next question, given that we're moving to a more consistent risk probability, is there any consideration of reassessing maximum horizontal direction? So that I believe is the same comment as before, or same question as before. So the next one, the previous NEHR provisions targeted a 1% probability class in 50 years. With the recent updates in regions not affected by the deterministic cap, will design ground motions generally be lower? Additionally, was the shift to 1.5% probability driven solely by the implementation of the deterministic cap, or were there other considerations behind this change?
Good question. Sounds like we should discuss more. I'll just try to keep a brief answer. Yeah, where you don't have deterministic capping, increasing the target risk from 1 to 1.5% 50 years will lower ground motions. It doesn't do it by 50%. It's not a linear change. So the decrease in ground motion might be closer to 15 to 20%. And as I showed in one of my plots, we're also changing USGS hazard model. And it turns out that on average, some of that 15 to 20% drop is on average, being captured by some changes in the USGS hazard model. So it will depend on your particular location whether the ground motion actually ends up going up or down with the change both from deterministic capping in the 1.5% 50-year target risk and the 2023 hazard model. So really depends. That's the answer. Happy to discuss more, so feel free to email. I'll try to put my email in the chat.
So I think this next one's going to go to Sanaz. Given the 2023 National Seismic Hazard Model considers full catalog rates rather than declustered earthquake rates applied in previous National Seismic Hazard Models, what impact is this likely to have on risk estimates?
Okay, that is a very good question, but it's a bit too detailed for me to answer. It can be different at different locations. I heard that panelists from our last webinar are online. If Alison Chambly or Peter Powers are online, I think this question is better answered by them.
Or I saw Ned just turned his camera on.
Yeah, hi, Ned Field here. I gave a talk last week on the earthquake rupture forecast, and that's where we're advocating for not declustering for the purpose of hazard and risk metrics. The short answer is the differences, as Sanaz said, will depend on your hazard or risk metric of interest, in particular the return period you're interested in. But overall, the differences should be small compared to the overall epistemic uncertainties in the model in general. And I'll just add to the ping pong question that are doing a better job of representing the overall epistemic uncertainties will help stabilize the model as we go forward in the future. So that's a high priority. But again, on the declustering, it really depends. But I don't think it's something that you generally need to worry about, at least in comparison to all the other uncertainties in the model.
Great, thank you so much. Thank you so much to all our presenters, to Bob for moderating the Q&A, and to all of those of you who joined us for this webinar. If you have further questions or want to discuss the material more, you can reach out to the speakers. Their contact information is available on their USGS pages. So just a couple final notes from us. You'll see a survey pop up in the Zoom screen. You'll also receive that by email tomorrow. We really appreciate your responses, which help us get feedback that we use to design our webinar and other public education programs. You can learn more about EERI at our website and join us there. You can also donate to the LFE endowment if you want to support our reconnaissance and other educational programs. And then finally, once again, I just want to note that the webinar series is supported with a cooperative agreement from FEMA, by the LFE endowment funds, and by EERI members. So thank you all for being part of this. We'll share the recording on our YouTube account within the next week or so, and I hope to see you at many future EERI webinars.